Hello, my name is Laura Crosilla and I'm a researcher at the University of Oslo. This is the first of a series of videos on infinity in mathematics. Infinity in mathematics is a topic of my research grant funded by the Horizon 2020 program of the European Union. The infinite is one of the most powerful concepts in human history. And it is indeed a key concept in a number of research areas and disciplines. It is well known, it plays a crucial role in mathematics, but it is also a very important concept in philosophy, which has been addressed by some of the major philosophers of all times. It is an important concept, of course, also in the physical sciences, mainly because of its role within mathematics. And it is well known, it is also a fundamental concept in theology. The infinite, however, even if so fundamental in our life, is source of constant puzzlement. So we are always troubled in some sense by infinity. In this series of videos, I'm going to explore significant philosophical aspects of infinity in mathematics. And I'm going to share with you some of my thoughts on different conceptions of infinity and what I like to call critical views of infinity. In the first video, today's video, we are going to look at a number of paradoxes of infinity as a starter towards the topic of a whole series of videos. Before looking at paradoxes, however, I'd like to convey a feeling of infinity. What is the best way of doing that if not by what philosophers would like to call a thought experiment? So let's start. So let's start by thinking about something. You can think of anything you like. Let's suppose we think about number one. And let's now think of the thought we just had of number one. But then we can think again of the thought of number one. And we can think of this again and so on. So every time we can think of a thought we just had, all starting from our first thought of the number one. So it's clear that in this way we can go on and on and on and always think of something new. But suppose now we can think of all of our thoughts originated in this way, generating this way from the number one, from our thought on number one. But then when we say, okay, let's think of all of our thoughts generated in this way, this is again a new thought. And we can then think about that thought. And then we can think of our thought about that thought, and so on. So we can start again from scratch with a new series of thoughts. And we can again think of closing them off, or all of them, thinking about them, and going on, and so on. So this gives you an idea of infinity, the fact that we can never stop when we think about infinity, and that we can also add larger ways of thinking about infinity. So one way of putting this fact that we can always extend an infinite collection, we can always think about some more of its elements, is by using the word inexhaustibility. The infinite, in other terms, is inexhaustible. No matter how far we reach, we can always add more. Think, for example, of ordinary whole numbers, so number 1, 2, 3, 4, 5, and so on. So we can think of a very large number, 1 billion, and we can always add one more. You can think about 1,000,000,001. You can think of a bigger one, say Google, and we can think of something always bigger than that, which is Google plus 1, and so on. But even more interesting, we can not just go on adding bigger and bigger numbers, but we can think of smaller and smaller ones as well. So we can extend our number line in both directions. We can add and we can get smaller and smaller numbers as well. So we can think, for example, number 0, number 1, and number -1. Number 2 and number -2, number 3 and numbers -3, and so on. And we can always go on in both directions. What is clear from this thought experiment we had before and these simple considerations about all numbers is that an infinite collection has no bound or limit. So, and in particular the case of numbers, we can go on and extend the numbers as much as we like. So what is important to notice already now, and it will play a role in these videos later on, is the thought that there is a sort of clash or a tension between our finitude, the fact that we are finite, and the infinitude of the infinite. So the infinite is inexhaustible, as we just saw. It is unlimited. It is unbounded. But we are, on the contrary, finite, limited, and bounded. We are so different from this concept. And this difference is the source of a clear clash or a tension between us and the infinite. So this can be captured by the following picture that I draw, just to show this tension between the infinity and us. This tension has been expressed clearly by Hermann Vile, a very famous German mathematician, Hermann Vile, where when he wrote in a beautiful paper from 1930, that mathematics is a science of the infinite. And he also wrote the great achievement of the Greeks was to have made the tension between the finite and the infinite fruitful for the knowledge of reality. And this is what I really want to stress. We have this great tension between our finitude and the infinite. But this tension, at the end of the day, is source of improvement and source of fruitful knowledge, as we will see later on. And by the way, Hermann Vile was already, I already implicitly mentioned Hermann Vile before when I said that the infinite is inexhaustible, because inexhaustibility, Vile told us, is indeed the essence of the infinite. So I borrowed from Hermann Vile this notion of inexhaustibility as a characteristic of the infinite. But let's go to the paradoxes. I already said I will be talking about paradoxes. So the first question is, what is a paradox? So paradox can be defined as a statement, or sometimes you have more than one statement. You have a series of statements. And the characteristic of a paradox is that these statements, together with some apparently true premises, and by using seemingly uncontroversial reasoning, forces us to reach false or absurd conclusions. So we start from something which seems absolutely uncontroversial and true, and then we end up in troubles. We end up with saying something which troubles us very much. So a typical, perhaps the most well-known example of paradox is the liar, which goes as follows. So we consider the sentence L, which says of itself it is false. So the sentence L is the sentence L is false. So let's suppose now to see what happens when we try to reason in, again, a very uncontroversial way about L. So let's suppose, to start, that L is true. But then if L is true, since L tells of itself that it is false, it means that L is false. But then suppose then that L is false instead. well, it's clear that if L is false, then the sentence that says L is false must be true. Therefore, L is true. When we have reached a conclusion that L is true if and only if it is false. So, and this is indeed a key example of paradox. A paradox is indeed originated in this way, by assuming something obvious and clear and reaching an absurd conclusion. So that was just an example of paradox in general, but there are paradoxes which are especially connected with the concept of infinity. And let's look at the first one now. Our first paradox of the infinite is the paradox of Achilles and the tortoise. So this is well known. It's a paradox which was again proposed in the ancient Greek times, that already Hermann Vile told us about. And it is the paradox of which arises when we think of a competition between fast Achilles and the tortoise. So Achilles and the tortoise compete in a race. And suppose that the good friends agree that the tortoise, as it is much slower than Achilles, should get a good head start. Suppose so then the Achilles starts a little bit behind the tortoise, and the tortoise starts moving, Achilles starts running, and soon after the race starts, Achilles reaches clearly the place where the tortoise had begun. But that time, however, the tortoise will have advanced a little bit. So Achilles will have to catch up with the tortoise at that point. By the time Achilles reaches his new point, the tortoise has advanced a little bit farther. And so on. So the thought here is that if we think in these terms, it seems that we are forced to conclude that Achilles will never reach the tortoise. And this is indeed the idea of a paradox of the infinite of Achilles and the tortoise, in the sense that we are brought to this, almost what seems an absurd conclusion that Achilles will never reach the tortoise, however fast he is. So we can see this in a drawing. So if we're supposed to see from above the ground, where the path in brown where Achilles and the tortoise run, the tortoise starts ahead of Achilles. Achilles quickly reaches where the tortoise is. In the meantime, the tortoise goes a bit farther ahead. Achilles reaches that. Then the tortoise moves a little bit farther ahead. And by the time she does that, Achilles reaches that, but then she has gone on to move, or she has moved on a little bit farther, and so on. So however far Achilles goes in reaching and trying to catch the tortoise will always move a little bit ahead of it. So this apparently problematic conclusion that we see in this case is that, it would seem that Achilles will never manage to catch the tortoise. As is well known, today's calculus gives an elegant solution to this problem. However, this gives still a philosophical problem. And we will see in the next video how Aristotle, the Greek philosopher, answered to this difficulty. So let's move on to another paradox of the infinite, which goes under the name of Hilbert's Hotel. And it's a very amusing paradox. So here we have, the idea is the following. We have a hotel which has infinitely many rooms. And suppose that in this hotel, all the rooms are occupied. So let's see it as, imagine a hotel with infinitely many rooms, all occupied. And suppose then at some point a new guest, the guy here on the left-hand side with this guy here, arrives and asks for a new room. And then it's easy to accommodate this new guest because, again, the hotel has infinitely many rooms. So when the new guest arrives, it suffices that the guest who is in room number 1, this one now, moves to the next room. So from 1 it goes to 2. But then the person who is in number 2, this one, can go from 2 to 3. The one is in number 3 goes to number 4. And the person is in number 4 can move to number 5, and so on. So essentially, there is no difficulty in accommodating a new guest because every guest present at that point in the hotel can shift on one room, on the right, making room for the new guest. As the hotel is infinite, this is no problem at all. Okay, let's see another paradox. Let's think, this goes under the name of Galileo's paradox. And let's think of all the numbers, whole numbers, 1, 2, 3, 4, 5, and so on. Let's now think also of numbers which are square of whole numbers. So the number 1 is a square of a whole number, it's a square of 1. Number 4 is also a square number because it is a square of number 2. And then you can go on. So you will see, for example, the next square number is number 9, which is a square of number 3, and so on. So we have that number 4 is square root number 2, and number 1 is a square root number 1. So if you look at this in this way, it looks clearly that the whole numbers, there are more whole numbers than squares. And so the squares, when you have a whole number here, 1, there is a square, 1, where you have number 2, there is no corresponding square here. Number 3 is also not a square. So in order to get to the next square, you need to have a jump and go to number 4. And then again, number 5 is not a square, and so on. So it looks clearly from this way of looking at things that you have more whole numbers than square numbers. Square numbers are fewer, less than the whole numbers. This can be expressed in this picture, so where you clearly see the gaps here when there is no corresponding number. So to show you indeed that the square numbers on this line are less than the whole numbers on this line, apparently at least. So what Galileo realized is that you can think of things slightly differently, and then you get a completely different picture. So let's get all the whole numbers again, 1, 2, 3, 4, 5. But now think of the following thing. So you can start enumerating in the next line all the square numbers. So the first square number is 1, the second square number is 4, the third is 9, the fourth is 16, the fifth is 25. So we can now see that for every number, you can think of a corresponding square number. So what mathematicians will say is that there is a one-to-one correspondence between whole numbers and square numbers. So for every whole number, we can find a square number that corresponds to that. The first square number, the second square number, the third square number, and so on. So we seem to be able to pair whole numbers with squares by just doing this. And we can go on as long as we want. However far we go in the whole numbers, we can always find a square number corresponding to them. So this was an observation that Galileo Galilei, the famous Italian scientist, made. This an observation that appears in his Discorsi e dimostrazioni matematiche intorno a due nuove scienze from 1638. the way Galileo put this is that as follows. So we can only infer that the totality of all numbers is infinite, and that the number of squares is infinite, and that the number of the roots is infinite. Neither is the number of squares less than the totality of all numbers, nor the latter greater than the former. And finally, the attributes equal, greater, and less are not applicable to infinite, but only to finite quantities. So that's what Galileo concluded. So the thought Galileo had is that this surprising correspondence between whole numbers and square numbers shows that the usual concepts we have of equal, greater, and less are appropriate when we talk about finite quantities, but become very problematic when we start looking at the infinite. So the notion of the comparison between the finite and the infinite somehow becomes more problematic than comparing two infinite quantities becomes much more complicated and difficult than comparing two finite ones. So that's Galileo's thought. Indeed, this is probably, well, one should say there is not indeed a paradox. We see a little bit more about that in the next video, next time, but it goes under the name of paradox, again, because the conclusions that we draw from thinking about numbers in a standard way is indeed puzzling and looks quite absurd. So we seem to be able to, we seem to think that there are less square numbers than the whole numbers, but we seem also to be able to pair them so that for each number there is a square number corresponding to it. So we seem to get into a very tricky situation. So to these examples, these three examples of paradoxes of the infinite can be taken to highlight this strong, clash or tension between our finitude and the infinite. These paradoxes highlight the difficulties we have as finite beings in making sense of the infinite. And that's, in a sense, the idea also at the heart of Galileo's remarks. Okay, so I've reached the end of today's lecture or video. In this video, we have introduced the puzzle of the infinite, particularly by using, first of all, a thought experiment, which allows you to get a feeling of the inexhaustibility of infinity by starting to think about anything and reflecting on that as long as you wish. And whenever you try to close off and collect all your thoughts, you will have the possibility by just doing that to think of a new thought. I have then seen three examples of paradoxes of the infinite. The paradox of Achilles and the Tortoise, which goes under the name of Hilbert's Hotel, and then Galilei's paradox, which we just saw. So in the next video, we are going to see, first of all, Aristotle's distinction between actual and potential infinity, which gives a possible way of answering the paradox Achilles and the Tortoise. And then I will look at the notion of Cantorian infinity, which is much more connected with the last two paradoxes, Hilbert's Hotel and Galileo's paradox. Finally, I will introduce a different kind of paradox, which goes under the name of Russell's paradox, and see how that relates with Cantorian infinity. See you next time.